day, everyone. My name is Rebecca Lilly with the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Decommissioning of Nuclear Power Plants, a New Challenge of Energy Economics. We are grateful to our distinguished speakers for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services you can find at our website at iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speakers. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated time at the end of the webinar to read and answer them. And now I would like to introduce you to the first speaker, Christian von Hirschhausen. He's professor of economics at the Work Group for Economic and Infrastructure Policy at TU Berlin and research director at DIW Berlin. Christian, over to you.
Thank you very much, Rebecca. Thanks also for the other team members of being here, and thank you for your interest in this topic, which is kind of a new topic in energy economics and technology, and one actually that Hannes Weigt and myself, I think, in a discussion at the ERI session 4 or 5 years ago, thought it would be worth the while of asking for a project, and that's what we did. And we obtained funding from the Swiss National Science Foundation and the German Science Foundation, DFG, to work on decommissioning as an emerging field of research for energy economics. And so we have put together this session as a kind of intermediate presentation of results obtained, but also questions that are opened by this research. This is done by the University of Basel and Technische University Berlin. I will give a brief overview and then hand over to specific presentations by the team. First of all, what is decommissioning? Well, some of you may be familiar with the system good nature of nuclear power, which starts, of course, with the resources, the mining, etc., building of a plant, its operation, and also reprocessing nuclear weapons, etc. Decommissioning is conducted once a nuclear reactor is shut down. Very simple, except that this process is lengthy and expensive. We don't have precise figures that can be generalized, but we generally calculate $1,000 per megawatt. So for a medium-sized or normal-sized plant, it would be $1 billion. Historically, decommission has not played a very important role because the focus was on constructing and on operating plants. And in some cases, the combination of inexperience and insufficient planning led to undesired outcomes to the extent that, for example, the post-war plants, the graphite plants, are still not being decommissioned. The Calder Hall, for example, or the Marcoule plants in France, and also in the US. Looking at the statistics, we see that this is a very important topic. We see here reactor startups since the mid-1950s, and we see expected shutdowns. And of course, given that these plants usually have a lifetime of about 40 years, shutdowns are about to occur in large numbers. Even lifetime extensions to 50, 60, or in some cases, perhaps 80 years will not change it. We are estimating that for each decade in the next 30 years, there will be about 70 to 80 gigawatt of shutdown capacities, which makes this also a very big market, given about $1 billion or euros of expenses. So it is an important topic. And we can distinguish between different decommissioning strategies and different asset specificities that are involved in this process. With respect to decommissioning strategies, general differentiation that can be done is between immediate dismantling, which is the normal case, which is conducted once the plant is shut down, deferred dismantling that has the advantage to allow radiation levels to decline, but has a disadvantage that knowledge and experience gets lost, and then entombment, which is a kind of third best solution that is only done when you have problems like, for example, in Chernobyl, or you don't know what to do at the short term. It is very important to distinguish three phases in the process. The first phase is the warm-up stage, where you defuel the plant. So you take out the radioactive material, you dismantle machinery, steam generator, and you prepare for the hot zone stage, which is the one that is the most expensive, where also the most knowledge is being required, which regards the reactor pressure vessel and the biological shield, which contain the highest level of radiation. The third stage is then called the ease-off stage, where you get rid of the rest of the material, the buildings, and have two options. Either you release the site from regulatory oversight, which is called the greenfield solution, or if you leave some of the material or some of the infrastructure, it's still called brownfield solution. In any case, these are important industrial sites that are in high demand in general. So there's a value of hurrying up. Unfortunately, this is not always the case. We see here on the left hand, you see an overview of all decommissioning projects succeeded worldwide, and we see there's only 20 of them, 22 actually, which is not a lot given that 204 reactors were closed. Most of them happened in the United States, some of them in Germany, one in the Japanese research reactor. And you also see in this brown bars that decommissioning in some cases takes much longer than even the operation of the plants. There is music in this activity, as you see here on the right chart, where you have the country experiences between June 2018 and June 2022. You see, for example, for each of the stages that the UK has entered into a larger scale decommissioning program, that in the US there has been significant developments, and other countries are also approaching this activity. So it's a very timely moment to have this webinar. And we'll have three presentations here. Hannes Weigt will follow up by providing the overview of the country studies that we have been conducting together. So I hand over the floor to Hannes Weigt, professor at the University of Basel. Thank you very much.
Thanks, Christian. So let's steal the screen and move over. Come on. To basically the overview presentation here. So as mentioned, it's a joint project in Berlin and Basel. And what we did is basically had a look at the different countries in the world and see what's the structure down there. Obviously, given the time and language barriers we have on our team, we couldn't have a look at all the countries that have some nuclear reactors somewhere. So those were the 6 countries where we finished the review so far. So as you can see, it's a quite diverse mix with a heavy focus on Europe and the US. So within Europe, we have France, Germany, and the UK being more or less the largest players here, with a quite diverse nuclear history, I would say, and also a quite different standing about the future of nuclear there. So that's, well, the countries you're gonna need to take in anyway. Then we have Sweden and Switzerland. They are more representative here of the smaller scale countries that still have a strong nuclear share in there. But not like the big France or German case with like more than 10 nuclear reactors in there. And we have a couple of them in Europe, but also globally. And then, of course, there's the United States, the largest nuclear power fleet so far, with also the most experience when it comes to decommissioning up to now. So that's kind of the status where we are. Of course, the structure we developed here can and should be applied to other countries, and we welcome and invite everybody to follow up on that road. Maybe have a look at Japan, have a look at Russia, have a look at China to see how the structure is looking there. But that's where we currently stand. In order to have an overview of what actually is going on, we structured our review along 4 main directions. First, we're going to have a look at what's the organization structure in that country regarding the nuclear industry in general, and then the regulatory structures, the involved parties when it comes to decommissioning. The second part is then understanding how is the financing for nuclear decommissioning structured. So knowing that this is kind of a costly long-term business, ramping up enough money to get all that done in a proper time frame is one of the main central elements in there. So that's the second block. And then with production, we mean the actual decommissioning, because at the end, you have to do the job, as Christian said, with the different phases. And naturally, that's where data is not yet readily available, because we just have a small set of decommissioned reactors. But as you have seen, this is a growing market. And as economists, we are, of course, interested, how could that market develop? What could be structures emerging there? And also, our project is focused clearly on decommissioning. We can't ignore waste management. But we are not looking at a long-term final repository here in the sense of a lot of governmental intervention. It's always with the link back to during the decommissioning, you have to handle the waste of the nuclear station. And how's the feedback loop about what waste management is done in the country to the decommissioning structure available? I will now shortly jump over kind of the summary and main insights we had, and mostly identifying the research gaps for those 4 fields. So let's start with the organization and regulation. What we've figured out is basically that one central difference between the countries is the actual ownership structure. Not only in terms of whether the state or the government is somehow involved in the ownership or it's private firms, but also along the decommissioning timeline. The ownership can actually change who is responsible for what during the nuclear value chain structure here. And the big question is, okay, what are the feedback effects of that? So far, we can't say that much about the long-term potential implications on that, but there seems to be a clear difference, and we try to understand what could be driving factors in there. At the same, if you look at the organization structures, they are highly country-specific. So Mohammed and Alex will present the UK and the US later on, where you can clearly see that those individual structures have quite an impact of what can and cannot be done. Who are the actors that are responsible? Who is basically the one making the final decisions at what stage? And that, of course, has feedback effects how the whole decommissioning structures work. So even if we just look at 6 countries, the question is then, of course, with, for example, newcomer countries that still have to build up their nuclear decommissioning structure, what can they learn from that so that they may compare with countries that have a similar regulatory structure or compare with countries that have a similar ownership structure. So that's kind of the best practices we would like to have at the end. Second block, that's the financing question. And here just a snapshot to showcase the difference you see in the investigated countries. So in the middle, the internal, segregated, non-segregated, and external block. This is more or less this classical filling up some kind of fund over the lifetime of operation or beyond, so that you can finally decommission and take the money out of the fund. And as you see, all of our investigated countries use that as at least one element in there. What you also see with the public budget and the guarantees, there seem to be also other structures, how you can ensure sufficient financing. And different countries use sometimes more than just one method doing exactly that, like you see here with Germany and the United Kingdoms or the United States down there. So obviously, again, there's a difference in the structure, how financing is done. And the obvious question we would like to ask then is, okay, what does that imply for the success, the efficiency of decommissioning? One central question we post in there is actually the question of cost structures and the estimations, how costly is such a decommissioning? With just 22 data points so far, a good chunk of them being research reactors, we are not living in a large empirical world. Rebecca will later on present one approach that we can actually use to investigate that a bit better. And with a better cost understanding, of course, also the funding question will become easier to solve, because then you know whether you're too short or too much in funding in there, and what could be reasonable structures for filling up such a funding element. The question of financial liability is also a quite important one, because in the end, it doesn't help if you have all the money in there and it's not enough. A firm needs to step in and the liability basically stops there, and the taxpayer will have to step in at the very last resort. So the question is more or less, are there kind of securities from a company perspective that make that more likely to happen and maybe put out the wrong incentives? So the big question here is really, how should an ideal funding structure look like to ensure that in the end the job is done with not too much or too little money being spent along the way? Another thing that is easily linked and also to other energy market investigations, most of those funding structures are filled along the way. So if energy markets change, also the external conditions change, and what you expect to be filled up a long time may not happen in reality, or maybe even faster than you planned for. So the question about feedback loops from market developments into nuclear decommissioning is also a quite important element where we're currently still working on getting some more insights. Moving to the last two blocks, the production and the waste management. Let's start with the actual decommissioning. As already mentioned, there's a market in the growing. And the big question is, okay, who is active on that market? So will it be a kind of make decision, nuclear power stations just doing their thing, buying maybe here and there a little specialized firm, but being the one responsible for all of it? Or will it be kind of, yeah, let's go on a market, there's a specialized firm for going with nuclear decommissioning and they're gonna do the job. As we've seen, it's going to be a big market for the next couple of decades and likely beyond. So there is definitely interest for firms to specialize and go into that business. We clearly see that, but we also see different structures with more make or more buy elements in the different countries. And the big question here is, okay, what is influencing that? And what are potential benefits of maybe going more market-oriented pathway or going more with a firm internal structure? And as already mentioned, the waste management per se, we are not looking at final repositories here in a deep technical or governmental perspective. But what has become pretty clear in our investigation is you can't ignore it, because in the end, every decommissioning power station needs some waste management along the line, be it for low or medium waste, and in the end, of course, also for the high level waste. And those usually run into a barrier, as far as we have seen in a lot of the countries, because sometimes those facilities for storage are not yet there where they should be according to the time plan. So the management and coordination of this waste element, which usually is way stronger on the governmental side here, is quite crucial for a successful decommissioning structure. So you can't really look at them individually. And the success or non-success of a decommissioning can easily hinge on whether or not you have a proper waste structure in the back. And again, we're not even talking about getting the final repository in there. We're often just talking about the intermediate steps along the line. So this is just a snapshot. And the whole webinar is designed as giving you an idea of what we're currently working on, with the next follow-up presentations with ideas on organization, ownership, make or buy, as well as financing. If you're interested in learning more of what we're doing, all of the research is freely available. So you can either just jump to our project webpage on our University of Basel site here, or have both the reports and the survey that I just presented in short here, either on our University of Basel accounts or on the DIW accounts in Berlin, as freely available downloads. So feel free to have a look at that. We're also going to upload all the presentations here on our project webpage after the webinar, so you have access to that as well. With that, I would hand over to Mohammed and Alex for having a look at the UK and the US.
Thank you, Hannes, for the overview. I hope everybody can see my screen. My name is Alex Wimmers. I'm a research associate and PhD candidate at the Technical University of Berlin. And together with Mohammed, I'll be giving you a short introduction on some organizational models that we identified in nuclear decommissioning. To begin, we'd like to introduce some theory on transaction costs, and this theory is then used to identify and explain the different organizational models that we will show for the United Kingdom and the United States later on. So when we're talking about transaction costs, in this sense, we see that these costs are real resources that are required to create and operate institutions and are not directly linked to value creation, but occur when goods and services are transferred across separable interfaces. And this is what we definitely see in nuclear decommissioning, with either contracts being negotiated between nuclear power plant operators and specialized firms that were mentioned earlier, but also just in the organization, preparation, and gathering of information for the decommissioning processes to be conducted. So what are the dimensions of the transactions that we can see for nuclear decommissioning? The first hand, we see a high degree of uncertainty at the nuclear power plants, especially in regard to the on-site radiological contamination of buildings and components that cannot be known beforehand. Therefore, quite a lot of knowledge gathering is necessary in order to determine how what kind of tasks have to be conducted when, and possibly how much they will cost then at the end of the day. Then another dimension would be the frequency. Looking at nuclear power plants, we see that the fleets are quite large, and ideas are ranging around achieving some economies of scale through repeating certain tasks and standardizing some procedures. And finally, the asset specificity of these individual nuclear power plants also plays an important role during nuclear decommissioning, as even in countries that operate similar nuclear power plants of similar technologies, for example, pressurized water reactors, there is some difference between individual reactors of the same technology and even the same model that depend on the site and the technology at the end of the day. And this asset specificity limits the possibility of applying economies of scale and standardized procedures for every single nuclear power plant. Oh, excuse me. So Hannes already mentioned the big question that we are trying to answer in regards to organization and production in nuclear decommissioning, which is the question of make or buy. So how far does the vertical integration go in terms of nuclear decommissioning when nuclear operators or nuclear power plant owners face the challenge of nuclear decommissioning? So do they conduct the production themselves by gathering the knowledge that on-site workers already have and conduct decommissioning tasks on their own behalf, or do they contract individual specialized firms and companies for either individual tasks or maybe even for the whole process of nuclear decommissioning? And in the following couple of minutes, we'll be looking at two distinct markets that we identified in our research, namely the United States, mostly in deregulated markets, that showed an emergence of two very interesting organizational models, and the United Kingdom that followed a kind of hybrid approach until last year, and has now since moved to the make approach. So, and in these models, we analyze the organization of the first tier approach. So on the basically management area, we limit, we don't look at individual tasks that might be outsourced to specialists such as construction firms or demolition companies that might be local for the certain companies. Moving on to the nuclear decommissioning organization in the United Kingdom. From 2004 onwards, the United Kingdom had introduced a new strategy for nuclear decommissioning after having tried to sell the nuclear fleet, namely the legacy fleet consisting of mostly old Magnox gas-cooled reactors. And as this sale had failed, because the sale would have included liabilities and responsibilities for nuclear decommissioning and nuclear waste, in 2004, the Nuclear Decommissioning Authority, the NDA, that's seen here, was created and was tasked with overseeing and conducting nuclear decommissioning for the United Kingdom, for the nuclear reactors in the United Kingdom. And the NDA came up with this parent body organization scheme that had the goal to introduce some competition to nuclear decommissioning while keeping the financial liabilities with the state, actually. And so what was done is the NDA conducted tenders for 5 to 10-year contracts to third-party organizations that were labeled the parent body organization, who would then assume ownership of the site license companies that are the operators of the nuclear power reactors, and would assume this ownership for a certain amount of time. And this amount of time would then be reviewed after 5 to 10 years. And the idea was to increase efficiency and just reduce the financial burden for the government. At the end of the day, after first initial efficiency gains, the scheme was retracted, and now the NDA has returned to the so-called market enhanced site license company scheme. Reasons for this are specific to the certain site license companies. For example, at the Sellafield site, that was still today owned and operated by Sellafield Limited, it became apparent that introducing a new PBO every 5 to 10 years increased the information asymmetry and just resulted in extremely high discovery costs due to the high uncertainty on site. And for the Magnox Limited site license company, similar developments occurred, where the NDA found that the information and the uncertainty at the certain sites was just too high to be outsourced and renewed every couple of years. And so today we find this market enhanced site license company scheme that has the nuclear decommissioning for the UK legacy fleet in full state control, which is a full make approach, while some specific tasks are still subcontracted to specific firms and specialists. And with that, I pass on to Mohammed, who will give a short talk on the United States.
Thank you, Alex. Yes, when it comes to the US, there are currently 3 organizational models in play. We have the traditional or conventional decommissioning model, and we have 2 new emerging decommissioning models, the license acquisition and the license stewardship. And we are gradually witnessing this movement towards new organizational models. When it comes to the conventional model, what you have is a nuclear power plant licensee or owner undertaking the responsibility to decommission the plant. But typically what happens is that elements of the decommissioning project is outsourced to tier 2 contractors. This is the conventional approach. The license acquisition approach, which is one of the new organizational models, what you have is a specialist company coming into the picture and fully taking over the decommissioning project from the original licensee. And this usually, what happens is there will be a transfer of license, the operating license, transfer of assets, the decommissioning trust funds, and the real estate of the nuclear power plant, the liability as well, the liability for any decommissioning cost overruns, and the ownership as well. The specialist company has 2 options. It can either fully undertake the decommissioning project itself. This is particularly if it has the capacity and the expertise to do so, or it outsources certain portions of the decommissioning project to outside contractors. But what we are seeing now is a mixture of the 2, a combination of conducting this decommissioning project in-house and outsourcing some portions of the decommissioning project. The third model is a license stewardship approach. Instead of a permanent takeover of the nuclear power plant, the specialist company temporarily takes over ownership of the plant, mainly the license, the operating license, the assets. This will be the funds, liability. Again, here, the specialist company undertakes the decommissioning project, and once it's completed, it gets transferred back to the original licensee. At this stage, the decommissioning company will not take over any fuel. This will be returned back to the original licensee. Now, just to give you some additional insights into the players that are involved in these 2 new models. The first one, under license stewardship approach, you have Energy Solutions, quite a large, diversified company providing energy services, both domestically in the US as well as internationally, as you can see here in the UK. Now, one of the advantages of Energy Solutions is its extensive assets that it can utilize for decommissioning project. And this covers practically a large spectrum of the nuclear back end, including low-level waste facilities, waste processing facilities, transportation, logistics, and so on. So it can leverage these assets for decommissioning. For now, it has completed decommissioning of 3 reactors, Zion 1 and 2, and La Crosse, using this license stewardship approach model. And it's overseeing decommissioning at further 2 nuclear power plants, 3 Mile Island 2 and Kewaunee. One advantage of having such a huge asset base is the ability to complete decommissioning in a short space of time. And we have seen that with the decommissioning of Zion, which was completed in a short space of time in about 13 years. When it comes to license acquisition, Holtec is a major player here. And it's really well known for providing fuel management contracts domestically and globally. And it provides wet, dry storage technologies, spent fuel loading services, and so on. And crucially, it also supplies NRC licensed dry cask storages to nuclear power plants. So that's the regulated dry cask storage technologies. For now, Holtec is overseeing decommissioning at 4 plants, so this is still work in progress. And there are plans to construct a consolidated interim storage facility, but this is facing some legal challenges. What are the chances? What are the risks of specialized decommissioning companies? At this point, it's good to point out that these models are able to function quite well in the US because you have a number of factors that ensure it's able to thrive. One of which is flexible transfer of licenses from party to party, and there are regulations that govern that. Plant-specific decommissioning funds, which makes it easier for a private company to come in and undertake the decommissioning project. And you have, for now, federal government still providing compensation to nuclear power plant licensees for spent fuel management. These are just some of the factors that are driving these decommissioning models. There are advantages, definitely, one of which is time, the ability to complete decommissioning in a relatively short period of time, reducing costs. And this site can be reused for other purposes. The other advantage is, especially if these decommissioning companies are managing a number of nuclear power plants, there is the advantage of economies of scale and transferring learning from project to project. This is something quite important. Clearly defined waste management pathways. These specialized companies provide waste management solutions from dry cask storage, from storage technologies, low-level waste facilities, and as I've shown you just the slide before, possible consolidated interim storage facilities for spent fuel. But there are risks as well to these new models, one of which is safety and security. So these companies might be so focused on trying to meet targets, trying to hit timeline targets and cost targets, that there are risks in terms of safety and security. The other risk as well, if you take on multiple projects and there are cost overruns, the specialized company might not be able to handle that. And also the final risk is, by providing this waste management pathways, it sorts of limits the federal government to provide a permanent solution to nuclear waste management in the US. So with this, I hand over to Rebecca.
Hello, everybody. I will share my screen now. Review. Okay, can everyone see my screen at this time now?
Yes.
Okay, great. Thank you to the International Association for Energy Economics and for TU Berlin for organizing today's webinar. I would very much like to discuss with you a method that we've been developing at Uni Bas for verifying decommissioning cost estimates ex ante. So the idea being that before we're in a situation where we might have a cost overrun, can we change our contingency level to better reflect the risks of decommissioning? So you've already gotten a very good overview of what decommissioning entails, and also some of the risks related to costs. But I'll just reiterate a few important ones. Basically, we have an industry that's really not been tested yet. There haven't been so many decommissioned reactors. So experience is scarce, and also cost estimates are scarce. So we can't really validate how cost estimates are made. It's important to note that it's a very highly regulated industry, and also cost estimates are highly regulated. Particularly in the United States, there are a lot of different points of control where one needs to fill up these decommissioning funds, and to a certain extent, and so on and so on. But these regulations, again, have not been tested. So what we are doing is hoping to use information on the experience that does exist to create an empirical estimate of a contingency that would be more appropriate for the risks of decommissioning. So we've done this by coupling two different methods, the reference class forecasting method with the Wilks formula, which I'll explain in due time. And we call this our best fit reference class forecasting approach. And so the idea is that we could use this approach and in various settings and create a better cost contingency so that we can prevent these cost overruns from occurring and potentially becoming a public burden, which is one of the major concerns that drives our research. Okay, so reference class forecasting is a method that was developed by two psychologists who would actually propose that the causes of cost overruns are not as specific as we might believe them to be. We get stuck in our singular data world, which you can see here on the left, where we think about all of the dimensions of our particular project. And what Kahneman and Tversky, who you've probably heard of from other contexts, noise or thinking fast and slow, proposed that in fact, we are in a much more general world where people either overestimate or underestimate costs because they're overly optimistic about how well things will run. And this is, pretty benign, or in a more strategic misrepresentation way where you're trying to win a bid of a contract, so you might underestimate the costs. So using this lens, what they proposed is that you could take the example from other projects to uncover these generic trends overall. So they basically use the trends of multiple different, in our case, nuclear power plants, their experience to uncover sources of optimism bias or estimation failure. So here you see on the right-hand side, our distribution, cartoon of our distribution of different plants. They all have very different characteristics in the United States, where we source our examples from. But the idea is that overall, they provide a larger picture that's very, very useful in terms of estimating costs. So we developed a database, and that's maybe being a bit generous because there's so little experience, but we drew from 9 commercial nuclear power plants. It's important. The experience from 9 commercial power plants to make our reference class. And these power plants have been decommissioned over the last, I guess, 20 or so years, 30 years. And we paired the cost estimates that they're required to disclose through regulation with cost realizations that either we had to estimate through various regulated documents or through collected studies on decommissioning experience. We didn't use all of the commercial reactors in the United States because of data quality and also what agencies they were regulated by. So we wanted to have particular attributes all maintained across the nuclear power plants, in particular that all the power plants would be regulated by the Nuclear Regulatory Commission. Okay, so the typical reference class forecasting procedure you see here has a few points, and I've already told you that we would identify this relevant reference class. So what does this reference class do? So in particular, we would think about our particular power plant, whether it be in the United States or another country, and we try and collect a representative sample of very similar projects. This is the first step and one of the most contentious and difficult. It's kind of an art still, and they're still trying to figure out exactly how to verify these reference classes. Once you've identified a reference class, and I'm more than happy to discuss this in greater depth during Q&A, you would then pair cost estimates with realized costs. This is actually a very arduous and long task, because you need to make sure that the cost estimates correspond to the same project where you have realized costs. In particular, they can't contain additional contingencies or anything of that matter, because you would bias your cost overrun estimate in the end. So once you get through steps 1 and 2, you get to the easy part, where we generate this cumulative distribution function of all of our observations, and we rank them in order, as you see here, by cost estimates. So our sample of 9 plants ranges from the Zion plants with roughly -10% cost overrun, so this is a cost underrun, all the way up to Humboldt Bay, where you see a cost overrun in the ballpark of 125%. Okay, so once you have this cumulative distribution function, you can consider a risk preference or risk tolerance for how much of your population you're willing to see cost overruns for. So we have been working mostly with something called P80, which corresponds to a tolerance for a 20% risk of cost overruns in the population. So to find that here on the graph, you go on the y-axis all the way up to 0.8, trace over to the curve, and then down to the x-axis, and you'll see that corresponds to a empirical contingency of 57%. It should be noted that typically contingencies are on the order of 25%. Okay, so this is the method that's currently used in reference class forecasting, and we decided that we wanted to tweak it a little bit to not only say something a little bit different about our data, but also to consider our confidence in our data. So as you can see on the graph on the left here, we have our observations in red, the data points just as we did before, but now we're fitting them, instead of with a linear combination between the points, we're fitting them with a Gaussian adaptive kernel density. This is a non-parametric method which weights the data and provides a much smoother and better fit of the data. And what it does is that every step along your adaptive kernel provides more information about the whole set of data as opposed to individual points and their relationship. So here, what we see using this is that our contingency drops to 48%. So a bit more less conservative, but still in the same order, saying that roughly we should be thinking about contingency levels of 50% rather than 25%, given our current experience. The Wilks formula is also a non-parametric method that was developed for manufacturing. And the basic thrust behind the method is how many widgets that I'm manufacturing do I need to sample to be confident that the rest of the population of widgets that I've manufactured will conform to certain standards that I've set for them. So here you can see again our sample in the CDF. And we have various observations that we're looking at here. R1 corresponds to the observation that we have with the greatest cost overrun. And then R2 is the second greatest, R3 is the third greatest, and so on. And what we can say with the Wilks formula is, given our sample of 9 power plants, how confident can we be that 80% of our population that we haven't sampled all of, because of course they're not yet decommissioned, will correspond to a cost overrun of 124% or 72%, and so on down the line, all the way, you could do it all the way down to the first observation. And this provides us with some statistical confidence. And we can look at this in a variety of different ways. What we've done here first is we've evaluated the fleet and solved for the confidence level. You can see that on the furthest column in the table, confidence level. So we said, given our sample of 9 power plants, what is the probability, or what is our confidence level, excuse me, that 80% of our population will have cost overruns of less than 124%. And here we solve 87% confidence. Now, 124% cost overrun is not a very strict threshold. So what we need is a bit more data, unfortunately, to narrow this down and have a very high confidence level. But to some extent, we're here developing this method and recognizing that the more data we accumulate, the better these numbers are going to be. Still, this does give us some way to gauge how confident we are. So then we can consider also the Wilks formula by solving for the number of observations or the proportion of the population that we wish to see. So here in the upper table, you see that we've solved for the proportion of population, the furthest column. Given our sample of 9, and we're wishing now to have a confidence level of 95%, what proportion of the population will have a cost overrun of less than 124%? And here we see that is 72%, okay? So you can also flexibly here then solve for the sample size. So to give you an idea, if we wish to see how much of our population or how many power plants we need to observe to be 95% confident that 80% of our population will fall below the third largest cost overrun, we need to observe on the order of 30 power plants. Currently, we are about halfway there. So this is roughly half of the French fleet. So it's no small task, but the idea is that over time we can get better cost estimates. So just to wrap up what we've done here is that we have the first empirical estimate of contingency for decommissioning. So this is not just a estimation anymore. We're really using the data that we have to try and come up with a more scientific basis for our contingency estimation. This is really valuable for regulators and policymakers, and that's really our aim here, is to inform policy. I'll modestly say that we have the largest data set of nuclear decommissioning cost estimates and realizations paired together, where we're considering all of the tasks to be the same. And what's cool about this method is that we can also think about it for other industries. So again, cost overruns are very common in other industries where you have long duration complex projects, new builds for nuclear power, decommissioning, other industrial projects. And this is a very flexible method. So it can not only be used for an entire project, but you can also, if you have some reference class that corresponds to one aspect of your project, you can link reference classes together to get a whole contingency for a project that's built up from a lot of different dissimilar aspects. We have done that in other projects before. So we can use this for both cost overruns and schedule delays, which of course they're related, but one could also analyze those data in a different way. And eventually we would like to look at other industries that have an abundance of data to try and solve this reference class problem, that is how to choose a good reference class and be confident in your reference class, which is something that until now has not been totally addressed or adequately resolved. And then also to verify how large your reference class should be, because if it's too large, you maybe get too far away from project similarity. So what's the sweet spot of reference class size and so on. So we'd like to validate the method a little bit more robustly with more data. So with that, I would say thank you very much for your attention. I'm happy to answer any questions that you may have. And please, if you're interested in digging into this method more, we have a working paper that's out. Our peer-reviewed paper is currently in review. But please go to the website that Professor Weigt provided earlier, and you can link to the working paper and read more about this topic there. So again, thank you very much, and looking forward to your questions.
Okay, I think we've done a intensive tour of the issues, and you have the possibility to put questions in the Q&A. We have slides will be distributed, of course. We have one question here to explain about firms specializing in decommissioning. Probably we have some experience from the US, Rebecca, or from the UK. Will there be multinational, government-backed? Will firms and countries having to decommission first have advantage due to gaining experience earlier? Becca, you want to say something about the nature of the firms engaging in decommissioning?
Sure. So there are a couple of specialized third-party decommissioning firms in the United States in particular, and they do work internationally as well. But these firms are largely vertically integrated and benefit from a wealth of knowledge from doing it themselves, and they basically move their workforce around to complete projects. So some people are for this, some people are against this. I would say that they have a very large advantage in terms of their ability to do things quickly, safely, and effectively, and at a lower cost, because they stand to benefit from earning the money that they don't spend. I would also say that in terms of the risks that we face, depends very much on the regulations of the countries they're operating in, of course. So in the United States, a company like Holtec that would be taking over the assets of a nuclear power plant, they have to prove that they can pay for decommissioning, not only with the funds that are set aside by the power plant, but then they have to have contingencies over and above that. So it depends on how you look at it. Businesses can fail, of course, but I think the rise of third party shouldn't necessarily scare people. This might be a much safer and more efficient way of completing decommissioning rather than handing it over to the government, which, as we know, can sometimes be a bit more of a slow mover.
If I could just add, I think in general, I would second what Becca was mentioning. In Europe, for example, we have put forward the idea some time ago to at least open up the access to these projects, which are currently not only regulated at a national level, but in Germany, for example, it's done at the state level. So you have the state of Bavaria, state of Lower Saxony, etc. And we have companies, we heard about Energy Solutions, we heard about Holtec, we have Ion Engineering, etc., that contend to be up to a third more efficient by gaining economies of scale, which, given that some of these light water reactors are relatively standardized, is a plausible solution. So a priori, there's no reason not to try it and then learn from that, because as we've seen in the overview and as we also heard from the UK and the US, these are long-term expensive projects, and we want to make sure to have a most efficient way of realizing it within, of course, the context of safety that needs to be surveyed by the state and national organizations. Are there any other questions. I had one here that whether it was possible to identify best practice. What impact would standardization of processes have on expected cost? We are now exactly 1 hour into the webinar, so our team will still be around for a little bit of time. If you have to leave, we thank you very much for your attention. We had over 30 participants in this webinar on a quite specific topic, which is good. So we thank you for your attention, but we will still be around for probably 15 minutes and continue to provide answers. Alex or Mohammed, do you want to say anything about this issue of specialization? Standardization, I mean.
Okay, this is
Do you want to go? Yeah,
practice.
okay.
Please,
okay, this
please.
is something that is that we might be seeing in the coming years. Just to take an example, Holtec is applying standardized procedures and processes across all its decommissioning projects. And with this, the advantage is that you're able to learn between projects. Later on, you'll be able to transfer workforce from project to project. And this is something that we will likely be seeing in the coming years. Yes.
Yeah, I can agree on that, especially if we're looking, for example, to France, that has a rather homogeneous fleet of mostly pressurized water reactors. Then EDF also calculates with especially lower costs because they expect that there will be some standardization and just some learning that will be occurring. But looking at the experience today, especially with plants that are quite diverse or fleets that are diverse, standardization might be limited at least to similar plants. And there will always be nuclear power plants that have some specific technical challenge, and that will then result probably in some specialized approaches.
Christian, maybe shortly adding to the best decommissioning practice question. Well, that's the name of the project, so we should provide some answers to that. One answer is it looks complicated. It looks complicated because, well, as you've seen just with the US-UK snapshot here, but if you look at the reports, there are quite some differences in the countries. And so the best practices will definitely be plural in the sense that for what we know so far, it got to be tailored to the countries we investigated. So the likely more interesting follow-up question in a big sense is more like, what should countries that are more at the early phase of nuclear industry, so having started maybe all the reactors, but not yet started shutting them down again, do in preparation for that? So, and that's a bit the idea. We hopefully gonna finish some insights on that this year. Like, if you start out in a green field, what should you do and what you shouldn't do? For most of the countries we are looking at, they're not in green field at all. They're really in a brownfield area quite heavily, and they basically have to deal with the structures they historically have constructed more or less. But some countries out there can still adopt and adjust because they have a couple of decades ahead. And that is definitely an open research question along those lines. What should we recommend for those? Contrasting to what can we recommend from the experience we have in the countries we investigated. And as Becca has said, well, every year kind of brings new data available. So it's also an ongoing empirical part in here, seeing how maybe the cost data can be updated, maybe how different firms react to that. So we highly encourage other researchers to follow this line of research gaps we laid out and hopefully provide some answers. But we also hope to encourage industry participants to provide us with more insights, maybe questions we missed and elements we should investigate as researchers, because this topic is going to stay for at least my lifetime and likely beyond. So, and I definitely not going to provide all the answers in there. So please spread the word and help us providing insights and answers as well. And we hopefully get an updated kind of best practice so far by the end of the year, early next year, as a kind of survey paper again.
I just want to piggyback on that as well. And it would be to know what kind of best practices our research team can actually provide. So we are really not in the realm of providing any sort of best practices in terms of technical know-how. This is something that's already in progress amongst the engineers and the nuclear industry, power plant operators and so on. And they are accumulating a lot of best practices. And to my knowledge, they are sharing to a great extent with one another. But we're largely looking at the organizational and economic factors that could be best practices for setting the incentives up correctly and setting up the institutions correctly so that decommissioning can occur smoothly.
We have another question by Jeff. Are there any insights into how extending the life of a plant influences its later cost for decommissioning? I'm not sure that there is any, given that we have 22 plants that have not been really extended in terms of lifetime, we have any firm evidence on this. What I would say is that the cost of lifetime extensions being highly distributed, but rather on the costly side, this is the more important factor when you consider lifetime extensions. Let me recall you that in France there are discussions ongoing of extending from 40 to 50 years and probably even beyond to 60, which costs about 100 billion euros overall, the so-called Grand Carnage. Understand that there's extensions being discussed in the US, of course, in Diablo Canyon and others. So my experience, without having been able to quantify this, is that these costs are more significant than the decommissioning costs. Of course, what Hannes Weigt has mentioned is true for all projects. You need to make sure in time to make provisions, both technically and also financially. And we have not talked about research reactors, which are not so much part of this project because they are really idiosyncratic and specific. And we have not talked about the legacy fleet of older reactors, in particular, as I mentioned in the introduction, the graphite reactors that are still standing around with no place to go, as they say. So there are topics that are probably more on the technical side than what you do with the graphite, what you do with the research material, etc., but which add to the need of solid financial resources. Otherwise, they will go on the public budgets.
Shortly adding to that question, basically, well, we don't know anything on cost of decommissioning, but one could make an estimation that if you now prolong the lifetime, you may basically start your decommissioning in the later phase of the market for decommissioning, which, if we still expect to see some efficiency gains, some specialized firms materializing and basically making the whole process cheaper, it could actually be that basically starting later could lead to doing it cheaper. But we have no empirical evidence on that, of course. I think the more important question with the lifetime is more like filling up the funding. So because most of the funds are basically filled up during operation. If you have 10 or 20 years more operation, you have 10 or 20 years more time to either get interest rates at least, well, nowadays we get them again, or make profit on the market. So that could also be an argument, not so much from decommissioning cost itself, but maybe they need to run a bit longer to fill up enough of the funding structure, because If they don't run longer, they need to spend the same or provide the same money in a shorter time frame, which could be a challenge given market conditions. And extending that may lessen that challenge, but then there are other arguments that may talk against extension in the first place. So it's a complicated issue that is coming from market developments. On the one hand, political influence, because there's a lot of political drive in whether or not nuclear is shut down or kept online. And decommissioning is more on the, I would say, funding side, not so much on the cost of decommissioning side, that this lifetime extensions get into the picture.
I would add to that by saying that when the way I interpreted the question was, are there technical sources of increased costs for decommissioning if you extend the lifetime? In the US, we're well into lifetime extensions. Most plants have already received their first lifetime extension of 20 years. And we have to think about is the source of costs in decommissioning largely come from the hot zone. So decommissioning the radioactive components of the plant. So how would that change if you extend the lifetime? I think the significant ways that I can think of off the top of my head without being a full technical expert on the area would be that you have additional fuel that you may not have adequate storage for. So I know that there are some power plants, for example, in the United States who have had to move their fuel to what we call independent spent fuel storage installations, so that they could cool more fuel because they have a longer lifetime than they anticipated when the plant was built. So that's an additional cost that would be incurred. Other additional costs would be in terms of decontamination. And my instinct, although this is an instinct and not coming from a huge technical basis, would say that the additional contamination that might occur over 20 years is not going to compose a make or break deal for decommissioning costs overall. This is going to be marginal relative to the full cost of decommissioning. On what basis do I say that? Well, for example, the power plant at Shippingport operated, that never even came onto the grid as far as I can recall. And its costs for decommissioning were much, much higher than some plants in the United States that operated for a long time. So let's be careful not to make this linear relationship between operation time and decommissioning costs, just like you can't make a linear relationship between capacity of the power plant and cost for decommissioning.
Okay, are there any other questions?
One just came in, which is basically would the feedback on decommissioning costs potentially impact the feasibility of new nuclear projects, especially with the repository for waste management in the back? So trying to answer that one out of the cold. So if we look at the existing fleet in the countries we looked at, they have been constructed in a time when basically decommissioning was not really on the agenda. So yeah, they knew at one point they need to decommission it, but it was not part of the decision to construct nuclear or not. So now that we basically enter the phase of decommissioning power stations, we learn more about the costs and learn more about the provision we need to do there. And new constructions likely need to address that now upfront a bit more clearly than like 50 years ago. And there it could potentially make an impact in both directions. It could be that the more experience we get, we actually figure out, yeah, well, the actually decommissioning is not as costly as we assumed. Once the firms learned a bit more, this process got standardized, the costs are kind of manageable. You have now a real number to plan with. So maybe that could actually help new nuclear projects because there's more security on that side. On the other hand, it could be the other way, that we learn all the problems we didn't have on the agenda so far, and costs are way higher than expected. So it's adding to the burden compared to just taking standard assumptions. So that's more on the direct decommissioning. When it comes to waste repository management, well, gut feeling in my lifetime, we won't have proper empirical estimates for those costs. maybe 1 or 2 observations, so case studies more. So there likely will need way more time to figure out how costly or less costly that may be. But my gut feeling again in this regard, not scientific backed, is the decision for or against new nuclear power stations will likely not hinge on decommissioning costs. It will be a political decision in most cases to either go along those lines or not, whether they see it as part of a decarbonized world or not. And whether decommissioning costs are higher or lower than maybe expected will not be the deciding factor there. The other numbers are likely more important, and it will be the political will to go or not go. But that again, that's me talking. That's not the scientist backing with papers here. That's just my general overview how I would see the picture.
Well, if you judge by experience that we have covered in the case studies, and once again, there's several hundred of pages available on the mentioned website, and referring to Becker's eco-psycho argument of optimism bias and strategic behavior, it's clear that companies tend to underestimate costs. We have I think in France, EDF is going along with about 300 euros per megawatt. In Germany, there are funds available, but the lifetime of the extension is being continuously extended. The picture that IEP has put on this webinar of Greifswald looming has just been extended. It was closed in 1990. At the time, it was thought to be finished in 20 years. Now the end is being pushed to the 2060s, which makes it about 70 years of decommissioning. Now, of course, you find specificities all over the place. This one is a Soviet reactor, so it does not correspond to the standardized fleet of West German reactors, but certainly taking into account these costs plays a role. There's an interesting aspect here with respect to the choice of the discount rate that in particular also applies to the waste of storage, to the issue of waste storage, because in the old days it was often said that, well, these costs occur so late they will be discounted anyway. But let me refer you to a paper of Professor Schulze that worked on Carlsbad and the WIP and the waste isolation plant, I think it was in 1981, that argued that in order to be sustainable, the discount rate should be set to 0. There are even people arguing for a negative discount rate. So in that case, of course, the cost of tomorrow, they weigh the same thing as they weigh today. So the costs of decommissioning and of waste storage are not being discounted away. We have another, probably last questions. Do we have any comment on some of the economic benefits of nuclear decommissioning, regional benefits, long-term employment, skills exports? Anybody wants to take this one?
Could start with a more general overview and then hand over to the experts, I would say, that are more deeper down there. In a sense, we're working a bit on related issues regarding the regional benefits or the regional impacts there. But if you look at nuclear power stations, there usually is a kind of small ecosystem around that during operation already. And so also decommissioning will kind of be seen as a small ecosystem that brings in money and jobs into the municipality structures there. But of course, there's an end time. So once the site is decommissioned, it's gone. And the question is more, what's the value of the site for general industry purposes? So maybe you want to push it faster to get into that new business. I think the interesting question regarding the value chain of decommissioning is whether they're going to be bottlenecks along the way for specific skills or specific parts, and whether specific firms can potentially really build up those skills and become the ones, well, abusing is maybe a harsh word here, but going into those bottlenecks and really be the one market setter there. Gut feeling is we don't have enough empirical data as usual again, But that could be an interesting investigation from a more conceptual perspective. And talking about the word export there's also always the question whether or not it's going to be a global market. It's going to be some US, some European, some Chinese firm taking over that business case if we allow that in the different nations. But now let's hand over to the more detailed experts. Alex?
Yeah, just to answer, maybe give an example for the on-site employment. It definitely depends on the type of strategy that is applied. So if you have a direct dismantling strategy, then most of the time the employees that were working at the nuclear power plant during operation stay on site, and the knowledge that they have acquired during operation is then used to the advantage of decommissioning, be it a make or a buy approach or something. So if there is not this deferred dismantling strategy that basically requires far fewer employees, as the nuclear power plant is just placed into long-term enclosure and just has to be monitored, the local impacts might be different. But as Hannes pointed out, at the end of the day, this new power plant will at some point be decommissioned, and then this ecosystem around operation and so on might be reduced. And in the United States, for example, we see with Energy Solutions and Holtec following different approaches. So Energy Solutions with the license stewardship has been observed to bring in their own staff mostly, while Holtec has actually incorporated the staff of the power plants that they acquired into their own company structure, just to gather this knowledge. And then these employees have stayed employed and have not lost their jobs at this specific plant. So it really depends on the strategy that's chosen, and then on the various plants, obviously.
Yeah, just to add a few points on the skills export, and Christian showed that we will be seeing a large number of nuclear power plants undergoing decommissioning over the coming years. So there will be a need for services, specialized services, human resources, tools, techniques. And so I think gradually over the coming years, the global market will play quite a significant role. And that's also for new nuclear incoming countries, because for now, based on our findings, we are not seeing much in terms of regulations on nuclear decommissioning and nuclear waste. So these ones will likely adopt this buy approach, where they head into the international market to source for skills. And touching on long-term employment, again, one new model that Holtec is applying is standardized procedures. So we might see again shifting of skills across decommissioning projects and the ability to be integrated seamlessly into these decommissioning projects. But this is early stages for now. So that's it for me.
Okay, I think we've done a good round. We had interesting questions. We still have people in the webinar, but we're supposed to close here. Let me just probably bring home three issues. One, the issue is important. It's a lot of money involved, a lot of technical expertise. So research is being sought intensively. There's a niche here. I think so far it's too early to speak about generalized solution, but I think that regulation and competition have a role to play here in terms of gaining potential productivity gains. And then third, something we have not really insisted upon but mentioned is that there's a link between decommissioning and the issue of storage. We've seen this with Holtec, we've seen this with timing of decommissioning that kind of sometimes depends on storage issues. We've seen it with the economics. So there's something that is further to be explored. Thank you very much for participating. thanks for linking to a IAE webinar. We have a European conference coming up in July. We have an international conference coming up next year in Istanbul. So stay tuned. Thank you very much, Rebecca, also for managing this webinar. And please check our websites for publications and ongoing research. Thank you very much.
IAEE would like to thank our speakers for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not already a member, we encourage you to join by visiting iaee.org. We thank you for attending. I hope to see you in Milan this summer, and I officially close this webinar.